Hello, everyone. Welcome to the Spring 2025 session of the Multi-Agent Learning Seminar. Today, we have with us Siddharth Nayak. Siddharth is a PhD candidate in the Aeronautics and Astronautics Department at the Massachusetts Institute of Technology, MIT, advised by Professor Hamsa Balakrishnan. He received his master's degree from MIT and his undergraduate degree in electrical engineering from IIT Madras. His research focuses on multi-agent robotics with an emphasis on reinforcement learning, graph neural networks, bandits, and language models. Today he'll be presenting his work titled LLaMAR. So take it away, Sid.
Yeah, so thanks a lot for the kind introduction. Today I'll be presenting our recent work, which is long horizon planning for multi-agent robotics. We call it LLaMAR because we use language models for it. If at any point you have questions, feel free to raise your hand or uh, I don't know, you can raise your hand on Zoom, I think. So yeah, I'd be happy to answer them. So I want to keep it as informal as possible so that it's you guys get to ask questions as well. Um, and before I start, I would like to thank all my collaborators with whom this work was done. It includes a few undergrads, people from industry, Google, Apple, Tesla, Stanford, and my advisor. Um, let's start. So there has been a lot of recent there have been a lot of recent works which have used AI for a lot of cool applications. And a few of them have achieved superhuman performances like chess, Go, poker. You can have these AI models do a bunch of stuff. But ideally, what do we want from AI? We want them to be really effective with humans, in the sense that humans should be able to collaborate with them effectively. For example, if you are working with Copilot or maybe ChatGPT, you should be able to have these agents try to help you out with things that you seem are important. And when you look at this inherently, it's a multi-agent system because you have you being a human as one agent and the other AI-based model as the other agent. It could also be you have multiple robots, and yeah, you have these multiple robots trying to collaboratively solve a task along with you. So let's consider the scenario where you have you have a few of these robots which have an arm around itself, and they could help you out with something. And you put out this intention that, hey, I want to prepare for a party. Can you help me out with that? And based on this instruction that you give, these multiple robots come up with different suggestions, which could be one of the robots says that, hey, I will go to the living room and start decorating it. The other one would say that I will go to the pantry and get some food, and it asks another agent for some help. The third agent says that, okay, I will help you with the food. Now, based on this interaction, the human would say that, cool, I will go and invite some of my friends, which means that based on these interactions, the human is able to create its own plan of actions. Um, so if you look at this problem is a long horizon planning problem. So long horizon planning, what I mean by that is each of these agents had to carry out a bunch of actions um, which satisfy the overall objective. Now here the objective is helping this human this guy to prepare for a party, and that could involve going to the pantry, picking up some food items, navigating to wherever the party is going to happen, keeping your food items over there, switching light. It involves a bunch of things, and each of these smaller subtasks involve um, a sequence of actions which needs to be carried out. So, for example, picking up something involves you controlling your joint angles so that it goes and manipulate picks up the item. Similarly, with navigation, you would need to do like an appropriate sequence of move ahead, left, right kind of actions to get to your goals. So this kind of uh, problem is a long horizon planning problem, and this is something that we would be trying to tackle on this. in this work. So if you look at this problem, it is a long horizon planning problem, but it also involves like a few other like research directions. Mainly, like it involves embodied robotics, where you have these multiple robots working in an embodied environment, which means that they need to interact with like real life objects and try to like make decisions based on like whatever they see. It is a multi-agent setting where you have like multiple robots, or like it could also be like a human robot collaboration kind of scenario where like they need to like do things in an effective manner. And also like there's an aspect of like human interpretability. Um, so as I said earlier, like the human was able to like make base its decision based on like what the other agents decided to do. So having this human interpretability is very important in these kind of like settings. So let's look at like why each of these things are hard. So embodied robotics, why is it hard? Like it involves you with like interacting with multiple like objects which require multiple skills. So the same robot has to like pick up something, open something, navigate to something. So it involves like multiple skills that you need to have access to. And it also involves like you grounding objects to language, which means that how do you teach like something is a bread or like something is a lettuce, and how do you like make sure that it does the appropriate actions with it? You cannot really open a bread or like open a lettuce, but you can like cut a lettuce, pick up lettuce. So it needs to like understand what kind of actions are actually feasible with something. The second problem, multi-agent robotics. I would presume that most of you would know like this is like there are like, a bunch of issues that show up. A few of them are like non-stationarity, where someone else's actions affect you. And there's also an issue of like partial observability, where um, like every agent is like looking at a different part of the room or like different part of the environment, and they don't really have like access to global knowledge. So the decisions need to be made are supposed to be made just based on your local like observations. Now, um, why is long horizon planning hard? So like if your environment is very dynamic where things are changing over time, or like you don't really know like what all things exist in the environment beforehand, you might need to like take care of that. Like uncertainty in the environment can cause like changes in the plan, which means that you need to be able to accommodate all these different changes in your plan and be robust to it. And like if you plan for like a big like long sequence, it might be possible that you might forget some of the tasks that were actually necessary to like complete something, which is quite similar to like how like most of us grad students work. So like one way like people like one major way in which people have tried to like address like long horizon planning is by doing hierarchical planning, where you have like a high level controller which splits up the task into smaller subtasks, and then these smaller subtasks are assumed to be like either traditional controllers or like maybe like a learned module which is specialized at doing something. Now this hierarchical planning setup does simplify things a lot, but like if you have like like most of the prior works, what they did was they like before the advent of like large language models, it would have been like tailored towards like a certain application where you would know how the environment works and everything. Now, if you want to like make it generalized to like bunch of like tasks, you would need some kind of like module that generalizes things, and that is where I think like large language models come into the picture. So let me talk you through like what people have done before with regards to using LLMs for like these kind of like problems, like long horizon planning problems. So you have like a human instruction which is fed to a planner language model. This planner language model is basically giving you a plan or a sequence of like tasks that the robots are supposed to do. These sequence of subtasks are fed into the controller. You feed it like you execute them in the like environment sequentially, and then you get the new observation. Now this is quite similar to how you would like plan for your next day based on like whatever knowledge you have about how your schedule might look like. So it could be like you're creating a schedule and then like you say that, okay, I'm gonna like do this, then I have this meeting, then I'm gonna get lunch, then I'm gonna like brainstorm with my lab mate and so on. So a major assumption here is that this does not really accommodate for uncertainties. So like in the timetable kind of like analogy, It's more of like you are working on something and then someone else in your lab had needed some help with debugging code and they wanted some help from you, but you didn't really have time to like accommodate for that time slot. And it also requires you knowing like all of the subtasks a priori before like even like planning, which might not be possible in like a lot of scenarios where you don't really know like how the environment looks like before. So a way to like mitigate this is basically doing reactive planning, where based on this human instruction, there's an actual language model, which based on like whatever the observation is, it creates like an action. This action is fed into the controller, which goes into the environment. You get the new observation. Based on this new observation, you create like a new scene description, which is fed back into the actual language model. Now, this basically reacts to the current state, where the current observation is solely determining what the action at the current step is going to be. But it does not really allow for like long horizon planning because you're just reacting at the current like for the current observation. And also like some of the prior works, what they did was this scene description. It relied on an oracle or like maybe a simulator to describe what the scene was and how much of the task have you completed. And the controller is assumed to be like a very good controller in the sense that like you just assume that it will successfully execute something if you tell it to do something, which might not be possible in real life cases. So this is where we introduce our method where we try to address this problem of like being able to react to the current state, being able to like plan for like a longer horizon, making sure that we don't really rely on on articles for both scene description and also like progress towards the completion of the task. And the controller, the low level controllers are not assumed to be like 100% accurate. So this
Sid,
is
I
like,
think there's a
yep,
question in the chat. Is
yep.
there a difference?
Is there a difference between hierarchical planning and a centralized controller? So centralized controller, in my opinion, could be like uh, could happen even without hierarchical planning. Um, so you could technically have this make this work for like single agents as well as multiple agents. But whereas hierarchical planning is more of like how do you split this task into like multiple sequences? Does that answer your question? If not, like just feel free to like interrupt me. But okay, so yeah, this is where we introduce our like algorithm, which is called LLaMAR, which stands for Language Model Based Long Horizon Planning for Multi-Agent Robotics. So similar to like what was happening before, you have an instruction and observation. This is fed into a planner language model. This planner language model is basically going to give a sequence of tasks that the language model thinks is feasible at the current with the current observations, and it gives you a list of like subtasks. Now this planner keeps track of like all the open subtasks and decomposes like the high level instruction into smaller subtasks. Then this list of subtasks is fed into the actor language model along with the observations and instruction. And it basically decomposes this subtask into a list of actions that each agent could carry out. So it's basically like assigning each of the agents with the action that it needs to take. I will walk you guys through like an example, like a working example, like after this overview. All these actions are then executed in the controller, and it's fed into the environment, and then you have the environment. So when you execute something in the environment, you get the new observation. Now, it's possible that at the current step, were able to like complete one of the subtasks that was actually necessary and was in the list of subtasks that the planner language model had created for you. Then you would feed this into the verifier language model, which is basically verifying whether something has been completed successfully or not. So all that it's doing is moving things from like a list of open subtasks to a list of closed subtasks. It's quite similar to like how you as a human being would have like a to-do list. You would like tick things off and like move it onto like the list of like completed things after you have like finished them. So based on this, you would update the plan. So verifier is basically allowing you to like keep track of things that have been completed, while it's not relying on an oracle for feedback. Um, Similarly, when you execute an action in the environment, it's possible that like the action, like the low-level control, actually failed to do something. So if it fails, like we pass it through a character language model. All that the character model is doing is basically reasoning on like what went wrong, and it suggests a corrective action. A thing to note here is that this corrective action is not immediately executed in the environment, but it's fed as feedback for the actual language model and the planner at the next step, so that it can make like a course correction to like make sure that the action is actually executed. So um, let's walk through like an example here. So here are like few of the things that like we initialize for an episode, and then we have these different modules that are being like um, used in the loop. So we have this language instruction, which is basically a task. So in this example, we would say that hey, fetch the groceries and place them in the fridge. Um, we have a memory, which is basically like a memory that keeps track of like things that have happened, things that need to happen, and so on, which is initialized as empty. You have the current observations, which is basically the two images from the two, like the point of view of like the two robots. You have a list of open subtasks, which is initialized as empty. You have a list of closed subtasks, which is initialized as empty. You have previous actions and a corrective action, which is also initialized as empty. Now you feed all of this as input to the planner language model. And based on the current observation, the list of open subtasks that the planner thinks are important is transport tomato to the fridge and pick up lettuce and place it in the fridge. So both of them are like making sure that you can transport the lettuce and the tomato to the fridge. As you can see in this image, there's a lettuce here and then there's a tomato, and these are the only two objects that it has seen currently. So this is fed to like this basically updates the list of open subtasks. Now, based on this update, all of this is fed as input to the actual language model. Now, the actual language model is going to like do things. So in the previous like slide, I like when I was giving an overview of the framework, I didn't really mention that we have a memory module also being outputted, being given as an output from the actual language model. So the actual language model is basically giving you a list of actions, which in this case is pick up lettuce and navigate to tomato. So it assigns like picking up lettuce to like agent one and navigate to tomato to agent two. And it also keeps like it keeps track of like the things that I've seen before and the things that it thinks is important for like making sure that it can use it sometime in the future. Now this is so if something fails, it goes to the corrector, as I said previously. So once you execute these actions, something might fail. So in this case, if it fails, you give it to the corrector. Now the corrector, what it does is basically reasons on like what went wrong, tries to come up with the reason, and suggests a corrective action. So in this particular example, picking up lettuce failed, which meant that it had to like reason on like why did it go wrong, and this is the reason that it comes up with. Hey, like it says that Alice failed to pick up the lettuce because it was not really close enough to it, so it should ideally navigate towards it before trying to like pick it up again. So this is fed up feedback to the next step, and the agent is able to like figure out, hey, I need to like do this before picking it up. Similarly, you have this verifier, which is ensuring that like keeping track of like things that have been completed. So right now, like when you execute these two actions, you have not really completed the like, subtask of like transporting a tomato to the fridge or like even transporting a lettuce to the fridge. So it would say that we haven't really completed any of the subtasks yet, which means that we still need to keep it empty. But at any future step, when it completes something, it would move the thing from open subtask to the closed subtask. A thing to note here is that the list of open subtasks can be updated as and when you get new observations, which means that in the current step, you just saw like a tomato and a lettuce. But like maybe like in some future times that you come across like bread, then it would update the list of open subtasks with transport bread to the fridge. So you have this like thing like repeating over and over until like you actually are able to like finish the task. So we perform a few experiments here. The first one is on a list of like household tasks where we have like multiple of these robots trying to help do some generic household like things. So over here, another contribution that we make, like have in our paper, is basically we introduce a data set called MapThar, which is based on the AI to Thar simulator. So what we do here is basically introduce like 45 different tasks, each instantiated with 5 different seeds, and each of these like tasks are categorized based on the difficulty of the task, where the, um, the difficulty is based on how vague the instruction is. So it could be like as simple as like saying that put like bread, lettuce, tomato in the fridge, where you explicitly tell what items the agents need to interact with and where it's supposed to like put them. Or it could be like very vague in the sense that clear the floor by placing the items at their appropriate position. So it's the test of like how the language models are able to generalize to the ambiguity of the instruction that is being given as input. Um, Along with this, we also define a few metrics which are used to like create a benchmark where we compare a few different methods with which use like prompting methods, different planning methods for like these kind of tasks in the context of like household robotics. So before I go on to this, before I go on to like the comparison, I would like to point out like all these like prior works which we use in our um, comparisons, and the things that like exist in the prior works and things that don't really exist in the prior works. Basically, I want to point out that our method basically can create that like do dynamic planning, can just work in a partially observable system where it doesn't really need like all of the information from the beginning. It can do like failure correction where the assumption like we do not really assume that's like um, the low level controller is like 100% accurate, and it also does self verification without having to rely on an oracle. Um, Also, exploration is an important aspect in this because you like since I said in the previous slide that you don't really know like what all things exist in the environment. And for this, we introduce a heuristic, exploration heuristic, which goes as follows. So you have like these robots where you have this and this in the living room, and they are tasked with like finding certain objects. So based on this, like let's consider like everything from Alice's perspective. So if the agent chooses to explore, what it would do is basically rotate in 4 different directions and get 4 different frames. We pass this image through a clipped image encoder, and we get the corresponding image embeddings. Similarly, we have a list of open subtasks that the planner language model has come up with. We feed that all the each of these lists, like each of these items from that list, to the corresponding clip text encoder. So we get similar encodings for that. And what we do over here is basically try to like dot product this and sum it over all the open subtasks. And what we do here is basically try to like explore the direction which has which gives a higher score, exploration score. So the key addition here is that explore directions that are more relevant to the list of open subtasks. So if you look at this example, if the agent was trying to find a computer, it would move in the direction that has like a table, because laptops are more like probable to be found on a table as compared to like the floor or like the sofa. So the key idea here in exploration is basically trying to explore directions which are more relevant to the list of open subtasks. So as I said earlier, like MapCar, we introduced a few different metrics. The first one is basically success rate, where we determine if something was like if the whole task was completed. So it's a one if it's successful, if it's zero otherwise. Then we have transport rate. Transport rate is basically what fraction of the subtasks were completed. We have coverage, which is a measure of like what fraction of the relevant objects that you were supposed to interact with did it actually interact with. There's balance to measure how equitable the subtasks are distributed. This is more of like trying to understand if the agents are like doing like if it's to ensure that like not just like a single agent is doing all of the things rather than like um so it could there could be a scenario where like a single agent is doing like all of the like heavy lifting and this other agent is just like wandering across doing nothing. So a balance closer to one means that you are more equitable. And also like the number of steps, which is basically you want to like finish completing this thing as quickly as possible. So before I go on to the um, comparison, I want to show a demo where the human instruction was I want to put groceries in the fridge, which was the same example that I showed previously. And you have these two different robots trying to like do like put relevant objects in the fridge. So let's talk about comparisons. We compare our method with a bunch of like other methods. There's a more detailed table in our paper, but the key things that I want you guys to like take a look at here is comparing our framework with other baselines. We show that our method has better success rate as compared to like other methods. So splitting the problem into like different modules with the planner, an actor, a verifier, and a corrector allows you to like get better performance as compared to like naive methods. So like this modular architecture does help as compared to other methods. Um, if you use vision and if you don't use vision, there's again an improvement when you use vision. So if you're just giving input as text, it doesn't really work well. A major reason for this is the corrector, which basically reasons on like the thing that went wrong. The reasoning happens more on like the image, and that's why like the corrector does need like image input to like give you better performance. And the other thing is with exploration and without exploration. So if you have like the exploration module added in, which was what I defined earlier, you get an increase in the success rates as compared to like not having exploration. So the key takeaway is like exploration does help you find like relevant objects as compared to not having it. So here's an example of the failure correction module. So here, let's take a look at this first example where the actor's suggested action was pick up it, but it fails because it's really far away. So the corrective action that it comes up with is navigate to the plate, and the reasoning was similar to like what I showed previously, where it says that it should navigate closer because it's far away. Here's another example where the task was to put like this. It was the same task where I was trying to put a bowl, mug, and plate in the fridge. And the action suggested by the actor was put plate in the fridge, and it fails because the fridge is not really open on the left hand side. And it reasons that I could not really put it in the fridge, so you should ideally open it before putting it. So the corrective action suggested is open the fridge. Here's a table of like not like comparisons where we activate different modules. So the four different modules that I talked about, where we have an actor, we have planner, verifier, corrector. As you can see here, LLaMAR, which is activating all four modules, is quite close to like having planner plus actor plus corrector. The thing to note here is this planner plus actor plus corrector has an oracle-based verifier, which means that LLaMAR is able to like get similar verification as compared to like an oracle-based verification. So um, the language models are able to do well in this kind of like self-verification process. Similarly, like as we did our experiments in MapThor, we also do it in a search and rescue kind of setting where we have multiple drones working in an unknown environment. Each of these drones have like a partially observable view of the environment, and they are trying to find missing people in this environment. And there are like different like types of fires. What I mean by different types of fires is it could be either extinguished with water or extinguished with sand. And these fires do really spread over time if you don't really extinguish like them as quickly as possible. And there's a water reservoir to like pick up some water, and then there's a sand reservoir to like pick up sand to extinguish this. So we perform our like the task that these drones are like given are basically trying to find these missing people and trying to extinguish these fire as quickly as possible. So here's a like a comparison of like search and rescue. When we increase the number of agents, as you can see here, the success rate does really increase as you increase the number of agents, which does make sense because as you have more number of agents, you can split these things more efficiently amongst these different agents. You can like prioritize exploration. You can prioritize like some of the agents to like extinguish fires. Like ask some of the agents to like um, find the missing people, and there is like a trend which shows that you can get better performance when you have like more number of agents. So the key contributions that we have here is we have like a modular architecture called LLaMAR, which integrates planning, acting, correcting, and self-verification through distinct language model roles. It can create like long horizon planning, like it does well. But as I showed previously in our table, the success rates of the best performing model that we had was around 66%, which is two-thirds of the time. It's still not like as great as you would ideally want for like real life um, deployment. And I feel like there's a lot of like scope in like making these models better with better like modular architectures. And we also introduced MapR, which is a test suite and a benchmark on like language-based multi-agent robotic planning, which is based on AI to Thor. So some of the limitations of our work and like things that we want to try out in the future are so our method has four different language models being queried at a single time step, which is way more than like what other language model based methods require, which means that the cost of like running these experiments are high. There is a potential improvement that could be obtained if you make the planning horizon limit longer. So in all our experiment, we set the planning horizon to be like 30 high level decision steps. Um, Technically, you could relax that a little bit more to see if it's able to figure out what went wrong and make corrective actions. But for most of our experiments, we set it to 30 because we didn't really want to spend a lot of money on GPT-4. It has limited spatial reasoning, so all that the language models get as inputs are the vision, like the image input, the 3D like 2D image that it gets, and it's able to like it's supposed to infer like how far things are from its point of view, and it doesn't really do pretty well at that. So injecting some sort of like 3D information might help. And also like the performance is limited by the underlying language model, so there is a need of like fine tuning these language models by creating data sets and making giving like specialized like data for like fine tuning them. With that, like I would like to yeah stop and like thank you guys for listening. Let me know if you guys have any questions. I'd be like happy to like answer them.
Thank you, Sid, for the talk. Everyone can feel free to unmute and or raise hand and then ask a question. Um, in the meantime, I'll ask a question. So, what do you think would be the capabilities of the newer reasoning models? What do you think would be uh, the benefits or like the advantages or like changes that would have take place if we like take say one of the newer models that are coming up in the last few weeks?
Yeah, I think like better reasoning would so I think like the way in which like the major motivation with which we started our project was trying to see if language models can actually do things for us. Uh, so I think like even though like when you have all of that reasoning, they don't really know how to like interact with like day-to-day objects and understand what the effects of it are. So in all our experiments, what we did was it didn't really have that kind of feedback where if it makes a mistake in like the way, so it doesn't really understand how the world dynamics works. So keeping track of like the mistakes that it makes and using them to like make the models better is something that I think would be better. Um, and also like most of these newer models, they generally tend to work better in just text only paradigm. But if you want to make like these robots work in real world, you would ideally need like multiple modalities of inputs. So uh, yeah.
Thank you. I think Promise has a question. Do you want to ask it?
Yeah. Hi. Thank you very much for the great talk. It was very interesting, and I think you really articulated everything about the project well in a way that I could follow. So my question is more about the metrics you used in evaluation, specifically balance. So I think that in general, I've seen many multi-agent setups, like because I'm interested in multi-agent reinforcement learning. So many setups, like let's say SMARC, they use win rates, they use some kind of performance-based metric um, in in measuring like how effective the team performance was. So I was happy to see something different about like collaboration. So I was wondering if you could talk more about balance, um like how we came up with this formula, and there's like any previous work or something that I could look at to just get more information about
Yep.
this
Yeah.
formula.
So this was more of like just so the balance metric that we have here is a very naive way of like understanding if um so so let me explain like what this formula like what this looks like. So let's assume that like you have one agent doing all the subtasks and the other agent doing zero subtasks. In that case, like the minimum of like the things that have been completed is zero on the numerator and one is in the denominator, which means that the balance is zero. If let's say like if you have two agents and one of the agents did like five of the subtasks and the other one did like five, then like min and max both are same, which means that the balance would be one. So we just wanted to get a sense of like how the agents are distributing things, distributing not things like subtasks to for the completion of the high level instruction. Ideally, you could also use a more sophisticated like metric to like quantify all of these distribution on like how things are being distributed. One way to like do that is probably like as you said, use some kind of like performance based like metric to do that. What I would probably do is instead of like transport rate, you could probably do like number of steps that agent like each agent requires and try to get a distribution over that. You could also get like a standard deviation on how different is like any agent's um, performance as compared to like the mean of all the agents. That does really give you a good sense of like how well distributed the metrics are. Um, there is also like some work which I did with Jasmine, where we introduce fairness in a cooperative multi-agent reinforcement learning setup. If you want, like I could send you the paper link later, which has some information on like how do you balance performance and fairness at like the trade-off between like performance and like fairness and like a multi-agent RL setting. Does that sound good to you?
Yeah, that sounds interesting. Is it like the paper from RLC last year?
Yes, so it was at RLC last year at the workshop, but then we had like more experiments and we have like a journal version of it with more details in it.
Oh, that's interesting. Okay, I could reach out with that. If I could
Yeah,
get
sure.
your email or maybe try to see whether you're on LinkedIn or something.
Yep, sure.
Yeah. But I think like so just to be sure I understood what you said about balance. I missed some part of it. I was wondering if you could go over it again. So for example, if I have let's say 4 agents, right? So I think what I'm not clear about is what are we taking the mean and max over? So
Yeah.
if
So
I have
sorry, go on.
no, I was just saying like maybe let me explain. Let's try to ground it with a 4 agent case. So where I have like let's say I have 4 agents in my setup. If one agent did not do anything, and let's say one of the agents did 2 things, and one of the agent did one thing, like what am I going to take the mean over and what am I going to take the max?
So it's basically the min over the number of subtasks that each of the agents have completed. That's in this case it's 0.
Okay. Okay, I
So
see.
ideally you would want like each of the agents to like doing something.
Yes, I see how that makes sense. And this E is like, what does it represent?
It's
Like epsilon or?
the epsilon is basically a small number just to make sure that the balance doesn't blow up to infinity when none of the agents do anything. If none of the agents do anything, then the max is also 0, which means that like the computation would blow up to infinity. And it's just there for the sake of like making sure that you don't really blow things up in the computation.
Oh, I see. That makes sense. Thank you.
Yep.